Welcome to the fourth session of this exponential and logarithmic function series. In this session, we will demonstrate how to use the exponential and logarithmic rules to simplify exponential and logarithmic expressions, as well as to solve their equations and inequalities.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the fourth session of this exponential and logarithmic function series. In this session, we are going to focus on the technique how to apply exponential and logarithmic rules to simplify expressions, solving equations and inequalities. Example 1 has 4 simple logarithmic equations to solve. As for the first one, since logarithm base 2 of x equals 2, after transforming it to the exponential form, we have x equals 2 squared, which is 4. The second equation is logarithm base 5 of x equals 4. After transforming it to its exponential form, we obtain the value of x, which equals 625. The next equation is logarithm base 7 of 49. Since logarithm base 7 of 49 can be written to logarithm base 7 of 7 squared, so x equals 2. The last equation is logarithm base 3 of 1 over 27, which can be written to logarithm base 3 of 3 to the negative cubed. Hence, x is calculated, which equals negative 3. Example 2 is to evaluate an exponential expression. The result of 2 to the 3x minus 2 to the negative 3x over the sum of 2 to the x and 2 to the negative x, given that 2x equals logarithm base 2 of 3. Since x equals 1 over 2 times logarithm base 2 of 3, and according to the property of inverse function, we recall the relation of a to the logarithm base a of b equals b, just like logarithm base a of a to the b equals b. Hence, the exponential expression can be simplified to the result of 3 to the 3 over 2 minus 3 to the negative 3 over 2 over the sum of 3 to the half and 3 to the negative half, which can be further simplified to 13 over 6. Example 3 is to evaluate logarithm base ABC of x, given that logarithm base x of a equals 2, logarithm base x of b equals 3, and logarithm base x of c equals 6. Since logarithm base ABC of x equals the reciprocal of logarithm base x of ABC, logarithm base x of a plus logarithm base x of b plus logarithm base x of c equals logarithm base x of ABC, which equals 11. Hence, the expression of logarithm base ABC of x equals 1 over 11. Example 4 is to evaluate an expression of logarithm base 42 of 56 in terms of a and b, where a equals logarithm base 2 of 3 and b equals logarithm base 3 of 7. Since logarithm base 42 of 56 can be transformed to the quotient of logarithm base 2 of 7 times 8 to logarithm base 2 of 7 times 3 times 2. However, it can be further simplified to the quotient of the sum of logarithm base 2 of 7 and 3 to the sum of logarithm base 2 of 7 and logarithm base 2 of 3 and 1. Since logarithm base 2 of 7 can be transferred to logarithm base 2 of 3 times logarithm base 3 of 7, which equals AB, hence logarithm base 42 of 56 equals the quotient of the sum of AB and 3 to the sum of AB and A and 1. Example 5 is to evaluate the expression of logarithm base 36 of 45 given that A equals logarithm base 18 of 9 and 18 to the B equals 5. We are going to show 3 different approaches to simplify this logarithmic expression. For the first approach, we change the base to 18 for the logarithmic expression. So it becomes the quotient of logarithm base 18 of 45 to logarithm base 18 of 36, which also can be written to the quotient of the sum of logarithm base 18 of 9 and logarithm base 18 of 5 to the result of logarithm base 18 of 18 squared minus logarithm base 18 of 9, which equals the quotient of A plus B to 2 minus A. As for the first alternative approach, since A equals logarithm base 18 of 9, so 18 to the A equals 9. Therefore, 18 to the A multiplies 18 to the B equals 18 to the sum of A and B, which equals 45. Here we assume x equals logarithm base 36 of 45. Since 36 to the x equals 45, which equals 18 to the sum of A and B. So 36 to the x equals 18 squared divided by 9, or in parentheses to the x, which equals 18 to the 2x over 9 to the 2x, which equals 45. Therefore, 18 to the 2x equals 45 times 9 to the x, which equals 18 to the ax times 18 to the sum of A and B. Since both sides of the equation has the same base 18, we equate their indices and get x equals logarithm base 36 of 45, which equals the sum of A and B over the result of 2 minus A.
Here we continue work on the second alternative approach for example 5. Since logarithm base 18 of 9 equals A and 18 to the B equals 5, A equals the quotient of natural logarithm of 9 to natural logarithm of 18. B equals logarithm base 18 of 5, which equals the quotient of natural logarithm of 5 to natural logarithm of 18. Hence, natural logarithm of 9 equals A times natural logarithm of 18. Natural logarithm of 5 equals B times natural logarithm of 18. So, logarithm base 36 of 45 can be simplified to the quotient of the sum of natural logarithm of 9 and natural logarithm of 5 to the result of 2 times natural logarithm of 18 subtracted by natural logarithm of 9. Hence, the logarithm base 36 of 45 equals the quotient of the sum of A and B to the result of 2 subtracted by A. Example 6 presents an exponential equation 2 times a to the power of 2x minus 2 minus 7 times a to the power of x minus 1 plus 3 equals 0, and 2 is the root of this exponential equation. The question is to find the value of a as well as the rest of the roots based on the given exponential equation. It can be reduced to quadratic form, as it can be seen on the screen. After factorizing the quadratic form, we have the factorized equation of 2 times a to the power of x minus 1 minus 1, or in parentheses multiplies a to the power of x minus 1 minus 3, or in parentheses equals 0. When 2 times a to the power of x minus 1 minus 1 equals 0, based on x equals 2, we obtain the result of a, which equals 1 over 2. After substituting the obtained value of a, 1 over 2, to the equation a to the power of x minus 1 minus 3 equals 0, the value of x is obtained, which equals 1 minus logarithm base 2 of 3. When a to the power of x minus 1 minus 3 equals 0, based on x equals 2, we calculate that a equals 3. Then we substitute the obtained value of a, which is 3, to the equation 2 times a to the power of x minus 1 minus 1 equals 0. Hence, we find another root, which equals 1 minus logarithm base 3 of 2. In conclusion, when a equals half, x sub 1 equals 2, and x sub 2 equals 1 minus logarithm base 2 of 3. When a equals 3, x sub 1 equals 2, and x sub 2 equals 1 minus logarithm base 3 of 2. Example 7 presents two simultaneous exponential equations. 3 to the x equals 4 to the y equals 6 to the z, where x, y, and z are non-zero real numbers. The question is to make a comparison among 3x, 4y, and 6z. First, we assume 3 to the x equals 4 to the y equals 6 to the z equals a constant k. After transforming to their logarithmic form, we have x equals logarithm base 3 of k, y equals logarithm base 4 of k, z equals logarithm base 6 of k. After applying the base changing rule, we have the reciprocal of x equals logarithm base k of 3. The reciprocal of y equals logarithm base k of 4. The reciprocal of z equals logarithm base k of 6. Hence, the reciprocal of 3x equals logarithm base k of 3 to the 1/3. The reciprocal of 4y equals logarithm base k of 4 to the 1/4. The reciprocal of 6z equals logarithm base k of 6 to the 1/6. As we know, 81 is greater than 64, which leading to 3 to the 1/3 is greater than 4 to the 1/4. Similarly, based on the fact that 64 is greater than 36, we have 4 to the 1/4 is greater than 6 to the 1/6. Hence, we may conclude the inequality of 3 to the 1/3 is greater than 4 to the 1/4, which is greater than 6 to the 1/6, which is greater than 1. Now, we need to discuss the value range of k. If k is between 0 and 1, we have logarithm base k of 3 to the 1/3 is less than logarithm base k of 4 to the 1/4, which is less than logarithm base k of 6 to the 1/6, which is less than 0. Hence, 3x is greater than 4y, which is greater than 6z in this case. However, when k is greater than 1, we have logarithm base k of 3 to the 1/3 is greater than logarithm base k of 4 to the 1/4, which is greater than logarithm base k of 6 to the 1 6, which is greater than 0 in this case. Hence, 3x is less than 4y, which is less than 6z.
If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.